Welcome to the last lecture of Review of Structural Analysis 1. This is essentially a concluding lecture of this review. You see, the last class what we did is we tried to write displacement, force displacement relation for a truss member. And then we also mentioned that the purpose was not to write the expression, rather the purpose was to make a very important point. We will be doing this exercise in detail in the subsequent weeks, but the point that I wanted to make is, you see, when we if you recall some time back, we discussed that stiffness and flexibility does not carry any meaning until and unless we explain what are the forces and the displacement are associated with that stiffness, because stiffness essentially relates force and displacement. Then naturally, what are the forces and what are the displacement components we have in structure, that definition is very important. Right now, if you have for the first example in the previous class, where we have just we consider the displacement as the net displacement, net change in length of a member, then we had just one force, and this this load displacement relation becomes a scalar equation. Then if we instead of taking the net change in length for a member, if we have to find out, if we have two displacement component, one displacement is the displacement at one end and the displacement at the other end of the truss member. Then we have two displacement components and then two forces, the force at one end and the force at the other end. Then the two displacement relations, two displacement components are related to two forces through stiffness, which is not a scalar, which is a matrix, a 2 by 2 matrix. Right. So, this becomes a matrix equation, that is called stiffness matrix. Okay, and that stiffness matrix is essentially the building blocks of matrix method of structural analysis. Now, but again then that is not the end to it, because again we can go further and change the definition of the displacement. Definition may not be the proper word, change the direction of the displacement, the definition of the coordinate axis. Instead of now taking displacement along the longitudinal direction, you can take displacement along vertical and horizontal direction. If we do so, then at every point we have two displacement, one at horizontal and one at vertical. The two joints means four displacement components. And then naturally four force components, the forces in horizontal and vertical displacement at both the ends. And then four displacement components relate to four force components to a stiffness matrix, which is essentially a 4 by 4 matrix. Okay. Now, then what is the size of this matrix? That depends on what are the displacement components you take and what are the corresponding force components we take. But one thing is very important in this stiffness matrix, and I will just mention that property today, but without giving really any physical interpretation of that property, because let us first go to third week and review some of the concept of matrix methods, and then when we come to formulate the method for truss and then subsequently beams and frames, then we will again come back to this property of the stiffness matrix, irrespective of whether it is 2 by 2 matrix or 4 by 4 matrix, irrespective of what displacement components you take and what force components you take. This property is a very important property, and that remains same, and we will come to that property once again in the subsequent week. Now, you see, so if you recall, one of the the stiffness matrix for a truss, the stiffness matrix was K is equal to A by L 1 minus 1 minus 1 and then 1. Okay. And this is your for a truss like this, where we have it is U1 and here you have U2 and corresponding force 1 and force 2. Okay. So, this stiffness matrix relates force 1 and force 2, this is force F1 and then this is direction force 2. So, this relates force 1 and force 2 with U1 and U2, right. Now, what I was telling just now is, now instead of that, if we take two displacement component here, say U1, this is U2 and then this is U3 and then U4, and then correspondingly you have F1, F2, F3, F4. So, 4 displacement components, force components, then your stiffness matrix K will be a 4 cross 4 matrix. Okay. Now, in this case we have 2 displacement, 2 forces, 2 by 2 matrix. Now, see, there are other important properties of stiffness matrix, those properties we will not discuss now, but just a property which is very visible when we write this expression is, you see, what is the determinant of K? The determinant of K is equal to, if you take that is equal to 0. Now, determinant of K is equal to 0 means we have a force which is related to displacement like this. Suppose we know the forces, we have to find out the displacement, right. Now, this is the linear equation, that is a system linear equation, and then this linear equation, but if the determinant is 0, if the determinant of this matrix is 0, then really we cannot have the solution of this matrix, solution of this linear set of equations, right. But we have not done anything wrong while deriving this expression. So, we cannot question this expression is absolutely right given the assumptions of the structure, which is a very reasonable assumption. So, this relation is fine, there is absolutely nothing wrong in this relation, but then if this relation is right, then does it mean that we cannot really find out, for a given force we cannot find out displacement, because it is evident, as of now it is evident that if the stiffness, if the determinant is 0, then how do I find out the solution? Now, you put a star mark here, that is a very important thing. We will come back again why it is 0 and what is the physical interpretation of the determinant of stiffness matrix being 0, and then what is the mathematical interpretation of this determinant of stiffness matrix being 0, and what happens, what needs to be done mathematically and also physically. They both are consistent, what needs to be done so that we can have a solution of this equation. Okay. Now, and you can, if we do that, and it is not particularly for truss, it is true for whether it is a beam, frame, or any structural component, or even if it is true, if we move beyond matrix method of structural analysis, as I said, the more general method is finite element method. Even in finite element method, we will see that the stiffness matrix is determinant, it is singular, it is not the determinant of the stiffness matrix is 0, and it tells a very important story, and that story we will see in the subsequent weeks. Okay. Let us first, before we come to that point, let us first review the concept of matrix algebra in the next week. Okay. Now, so if we do it for beam, say for instance, if we take a beam problem, now suppose this is node number 1, this is point number 1, and this is point number this is point number 1 and this is point number 2. Okay. Now, at every point we have 3 degrees of freedom. If for a plane beam, if it is space frame, then at every point we have 6 degrees of freedom. Now, what are the degrees of freedom? Now, if we consider all the forces, means if we consider the force in this direction, means let us take a different color, means suppose it is U1 is the displacement in horizontal direction, then we have displacement in vertical direction, and then we have rotation of point A. So, we have rotation of point A, which is U3. Okay. Similarly, at this point also we have this is u4 and then u5, and then we have rotation at joints say u6. Okay. So, total 6 degrees of freedom we have. So, similarly, we have 6 force components, force F1 in this direction and F2 is, let us write the force components also. So, F1, this is F1 and this is F2 and then moment in this direction. Similarly, we have this is F3 and then we have F4 and then F5 and then moment F6. So, we have 6 components of forces and 6 components of displacement. The 6 components of displacement and forces are related to a stiffness matrix. Naturally, in this case the size of the stiffness matrix will be 6 by 6. But now again if we assume that there is no axial shortening of a member. So, there is the axial shortening is neglected. If we neglect U1 and U4, there is no U1 and U4. If we don't the axial deformation, if we neglect axial deformation, then we are left with, so then we have only 2 displacement, 2 degrees of freedom here. One is the displacement in this direction and the rotation at this point, and then again displacement in transverse direction and rotation at point. So, essentially then we have a 4 displacement components and correspondingly 4 force components. This the size of the stiffness matrix become 4 by 4. But again, irrespective of whether it is 4 by 4, 2 by 2, anything, the singularity property that just now we discussed, the determinant of the stiffness matrix is 0, that remains same. Okay. Now, just to give you some idea about in what way, consider let us individual displacement and then see what happens. So, if I take say for instance say U3, if I take U3, if I take say U2, U2 means your displacement becomes this. So, this is the structure and then this is the structure and your only displacement is u. So, all other displacements are. Then we can find out what is the corresponding forces, what are the so it is U2, this is U2. So, just now like the class problem, we considered individual degrees of freedom and wrote how these individual degrees of freedom is related to corresponding forces, and then we calculated what are the total forces at each node and get the stiffness matrix. Similar exercise you can do for beam as well. So, this is you have to take individual degrees of freedom, individual mode, all the modes separately, and then we combine them together. Similarly, if we take U3, then U3 becomes, if this is the original configuration, and then U3 is the rotation at this end, rotation at this end. So, rotation at this end. So, this is U3. This is U3. So, we write force displacement equation for U3 and then again we can do it same thing for U4 and U4, U5 and U6 for all, and then we have the force displacement relation, we combine them to get the stiffness matrix. But since we will be doing that in details, I am not discussing right now. So, let us now summarize what we have discussed so far and then move beyond. So, displacement the stiffness definition is the building block of matrix method of structural analysis. We have to write the force. So, we have to first we need to decompose the entire structure into small part. For each part we write the force displacement relation through the stiffness definition, and then we assemble, and every part, this relation, the force displacement relation, every part, the stiffness matrix, stiffness is essentially a matrix, and what is the size of that matrix depends on the what are the degrees of freedom we are considering. Okay. Now, once we have written the force displacement relation for all members, and the next thing is we have to assemble all these members to get the global individual stiffness matrix. Sometimes it is also called member stiffness matrix, because it gives you the how the member forces are related with each other with the displacement in a particular member. Once we have the member stiffness matrix, then we have to assemble all the member stiffness matrices and get the global stiffness matrix of the structure. And when we calculate global stiffness matrix of the structure, we have to consider the orientation of different members and how this connectivity different members all together. Once we have the global stiffness matrix, and then we have to solve it. But then when we solve it, some of the difficulties we may face, not the difficulties, some of the interesting observation we will see while solving those matrices, and those observation we will discuss, the interpretation of those observation we will discuss when we face it. Okay. And all these exercise, everything needs to be done through matrix operation, right. And therefore, it is very important to review the matrix operation, and that we will be doing in the next week. Now, once we formulate the entire the method for different structural components, for say truss, for beam and for frames, and then demonstrate that formulation through small examples. Next, you see there are two important motivation for looking beyond matrix, looking beyond structural analysis. One, the first motivation is that we need to solve very large structure where are different members, large number of members, large number of joints and different kinds of forces. So, scalability is an important factor, and the another important thing is the ability of the method to get translated into computational code. Okay. So, whatever formulation we learn here, this formulation really we do not do it manually. We have to write, at the end of the day, we have to write a computer code to do these operations, okay, to assemble, to write the stiffness matrix of different member, identify the orientation of different members, write the stiffness matrix for different members and assemble it, and then solve it. Suppose you have a for any truss, suppose you have 100 or say 500 joints, and every joints you have 2 degrees of freedom. So, 1000 by 1000 stiffness matrix you have. So, essentially you can have a very large number of stiffness matrix which cannot be solved manually. So, computer has to do it. So, we have to write computer code. So, what we will do towards the end of this course, we will spend 1 week to discuss various implementation issues. When we implement that method into computer codes, definitely we will give some example how to write it, what would be the structure, in what way we need to store the different variables. We call it stiffness matrix, but does it mean that we have to, when we really store that matrix in a computer program, we have to store that in a matrix form, or there are a different way we can store those variables to get to optimize the operation, to get the code faster. So, now those are the implementation and then translation into computer codes. Various issues related to that we will be discussing towards the end of this course. Okay. So, I stop here today. Next class, next week, the review of matrix algebra will be taken by Professor Vishwanath Banerjee. I will come again on 4th week, where we will formulate the matrix method of analysis for truss. Okay. See you. Thank you.